So, if we're looking at that sheet that I gave you guys on Friday, we're looking at the front page where we have homogeneous suspension solution and colloids on. Okay, so I just want to walk you back through that sheet one more time before we take this test. The homogeneous solution, I think you guys are good. I'm not going to go back into homogeneous solutions. Just remember that they look the same throughout. But there are 3 examples of homogeneous solutions that may not have been clear to you guys from the sheet. So 3 examples of homogeneous solutions. Homogeneous solutions. The first one, the one that's in the top right corner of your sheet, is a suspension. And so remember that the particle size dictates what type of homogeneous solution these things are. And so a suspension is one that has a particle size that is greater than 500 nanometers. And so if the particles are greater than 500 nanometers, they are temporarily suspended. So particles are temporarily suspended. Particles are temporarily suspended. And so what that means is pretty obvious. It means that the attractive forces that exist between the solvent, the water or whatever it's dissolved in, and the solute are too weak to permanently suspend them, and so the particles fall out over time. And so particles are temporarily suspended, and so if we had a quick little drawing just to reference this, we'd have a little test tube maybe, and we'd have some stuff that looks homogeneous currently, but over time, as time progresses, these particles fall to the bottom of this test tube. And so they would all collect down here, okay? And so that would be indicative of a suspension. Some quick examples of these things. I think we talked about paint as being one of them. So an example would be paint is a fine example. Maybe if you like a little chocolate syrup action in your milk, that would be a good one. Some chocolate milk would be fine as well. So suspension, that's it. Solution is smaller particles. A colloid is smaller particles, not a solution. I want to do colloid. So colloid is smaller particles. We're talking particles between 2 and 500 nanometers in size. And so these are where particles are permanently suspended. Particles are permanently suspended. And why they're able to be trying to learn how to spell permanently suspended, is because these particles are small enough that the attractive forces that exist between the solvent and the solute are strong enough to prevent them from falling down. So the bonds that exist outweigh the particles want to fall out of solution or suspension. And so they stay permanently suspended. And so what would this look like? You would have a test tube again, and you would have a bunch of stuff dissolved. It looks homogeneous throughout, and it remains homogeneous throughout over time. And so you might have particles again. They stay suspended permanently, okay? And so those are colloids. Example being something like Jell-O is a fine example of a colloid. It's probably the one that we can all relate to most often. The third one is a solution. A solution is less than 2 nanometers in size. And so what happens here is that the particles are dissolved in the solution. Particles are dissolved. Dissolved in a solvent. And so remember the solute-solvent relationship. Solute is what is being dissolved. The solvent is what is dissolving. So best example perhaps is if you had lemonade powder and water. The lemonade powder would be a solute and water would be the solvent. Okay? And so what happens here, the one thing that I wanted to make sure we talked a little bit further is I don't know how comfortable we are with the word dissolved. And so I wanted to make sure that you guys understood this. This was my big concern, is that you guys understood what dissolved meant, because it was so, it was kind of ubiquitous throughout all of the topics that we discussed, including conductivity. And so I wanted to make sure you guys understood that wherever we go, dissolved is going to be kind of fundamental in your understanding of this. And so I wanted to elaborate a little bit further on what dissolved meant. And so dissolved, if we had sodium chloride, right, if we had NaCl and we dropped this into solution, if we dropped NaCl into solution, dissolving means that it separates. So that you have Na plus ions and you have Cl negative ions. And so when that separates, water kind of wedges itself between sodium and chlorine, and that's what causes it to separate out. In the picture that I drew at the bottom right corner of the paper, if you guys are referencing that, the picture that I drew at the bottom right corner is drawn out for you. It shows sodium at the center of it, Na plus, and it shows chlorine at the back of it, Cl minus. And so, as a result of that, those charges have become separated, and that shows you that it has been dissolved. So you can see that there's H2O sandwiched in between each sodium and each chlorine ion. Does everybody, we see that in the picture, I hope? Everybody's cool with that? Okay. So, the next thing that I wanted to make sure that we understood was solubility. And understanding factors that might influence solubility. So let's talk quickly about that. Is it going to clear? Okay. Solubility. So solubility, let's be clear, is the ability of one substance to dissolve in another. Ability of one substance to dissolve in another. One substance to dissolve in another. So, for solubility, it is dependent on three things. So we can get a substance to dissolve faster. Three factors that influence solubility. Three factors that influence solubility. The first one, I think you all know this one, is temperature. If we increase temperature, an increase in temperature equals an increase in solubility. And that is because particles move faster at higher temperatures, and so they're able to expose themselves to more of the solvent, and thus it just dissolves a lot faster for that reason. It's very straightforward and self-explanatory. The second one is surface area. Surface area. With surface area, an increase in surface area equals a increase in solubility. So for surface area, we think about those sugar cubes at a restaurant. I think we all have some type of idea as to what those sugar cubes are or what they look like. Those sugar cubes. So as surface area goes up, solubility goes up. And so we think about the sugar cubes at a restaurant. Those cubes, if they remain whole and you try to put them into your beverage at the dinner table, they will dissolve very slowly. And it's because they have a low surface area. If you took the time to crumble up that sugar cube and then drop it in the water, it would dissolve at a much faster rate. And so think about that when you guys are contemplating what factors influence solubility. If you break up those particles into a smaller size, it's increasing the surface area because it's exposing more of the solute to the solvent. If you thought about a sugar cube, all of the sugar that's on the inside of that cube isn't exposed to the solvent. And so by breaking it apart, you're exposing more of it. That is increasing the surface area, and thus you're able to dissolve it faster. The third one is stirring it. And this one is obviously straightforward. I don't even think I need to write the relationship for you. If we stir a substance, it's exposing more of the solute to the solvent. By mixing it up, you're able to expose that solute to more solvent. It's pretty straightforward. So I guess if we were to write a relationship, if you increase stirring, you would increase the solubility. That makes no sense. So know though, please, that these three factors influence the solubility only for gas, liquids and solids. Only for liquids and solids. Okay, this part. That is only true for liquids and solids. For gases, it's entirely different. Gases solubility decreases as temperature increases. Okay? That is something that is very important for us to remember. So if you think about those solubility curves that we did, there were two lines that went down. I hope you guys remember that. Those two lines went down because they were in the gaseous state of matter. And so the gase's solubility was decreasing because the temperature was going up. You guys will need to be able to recognize that in the solubility chart. Understanding that the lines that are going down represent gaseous states of matter. Okay? So that will be important for our test in a couple of days. So gaseous solubility decreases as temperature goes up. The only way to increase the solubility of gas is to increase the pressure. The only way to increase solubility of gases is to increase pressure. And by increasing pressure, what I mean is that if we had a little piston, perhaps, if we had a little piston, something that was going to be pressed in a downward motion and kind of squeeze those gas particles together. If we had a gas in here, so this is the gas currently. If we, that's not what I wanted to do, guys. I wanted a test tube. Sorry, let me erase this. So if we had, I don't know how to draw this. I do, we're good. If I had water here, and we had a piston up here, the gas particles will hover above this liquid, and then there'll be some particles, obviously the liquid particles suspended here. And so this piece is the gas, this piece is the liquid. If we increase the pressure, so if we increase the pressure, you would have very little room above the water because the piston has shrunk, so the volume that gas occupies has decreased. And so you will have some particles here, but a lot of them will have been pressed into the water or into the solvent. And so in this case, they have dissolved more due to an increase in pressure by squeezing them and forcing them into the solution. And so we can relate this to Coke cans. Increasing the pressure will force carbon dioxide. That's what carbonation is. It forces that into the water. And so when you guys open a Coke or you go to a vending machine, all those bubbles fizz out because all of the carbon dioxide is leaving due to a decrease in the pressure. Okay? Everybody, we cool? I'm done here. All right.